Thank you all for joining me. I'm excited to dive into a topic that plays a crucial role in the world of machine learning, support vector machines, or SVM. Throughout this presentation, we'll explore what SVM are, how they work, and where they are applied in real-world scenarios. We'll also discuss the key advantages that make them so powerful, as well as the limitation you need to be aware of when using them. By the end, you should have a solid understanding of when and how to leverage SVM in your own work. Let's get started. Let's talk about something pretty fundamental in the world of machine learning, support vector machines, or SVM for short. Now, at its core, an SVM is a supervised learning algorithm. And what that really means is that it's a type of algorithm that learns from labeled data. So, for example, if you want your computer to distinguish between different types of emails, like spam versus legitimate emails, you'd feed it a data set where each email is already categorized, and the SVM would learn to make those distinctions on its own. But what's interesting about SVMs is their approach to separating data. Imagine you have two categories of data points. Let's say one group representing spam emails and the other representing regular emails. What SVM does is it tries to find the best possible boundary that separates these two groups. And when I say best possible boundary, I'm referring to something called the hyperplane. This hyperplane is designed to maximize the distance between the two categories. It's kind of like drawing a line in the sand that's as far as possible from both groups. This helps reduce the likelihood of misclassification. The beauty of SVM is its versatility. You can use it for a wide range of tasks, from face recognition systems to predicting future trends based on historical data. It's especially good when the boundary between categories is clear, but it can also handle more complex overlapping data by using something called a kernel trick. But that's getting a bit into the weeds, so we'll keep it straightforward for now. Ultimately, SVM's goal is simple. Find the most clear-cut and distinct boundary between categories of data so that the algorithm can make accurate predictions in the future. So now that we have a basic understanding of what an SVM is, let's dive into how it actually works. The core idea behind SVM is all about drawing a line, or more generally, a boundary, that separates your data points into distinct categories. Let's keep the example of spam and non-spam emails going. Imagine you've got these two groups of emails as data points plotted out in space. What SVM tries to do is figure out the best way to draw a line, or hyperplane if we're talking more than two dimensions, that clearly divides those two groups. Now, here's where it gets interesting. SVM doesn't just draw any line. It's looking for the line that creates the widest possible gap or margin between the categories. This gap helps ensure that future predictions are as accurate as possible. The wider that margin, the more confident the model is when making classifications. It's a bit like saying, I want to be as far away from both groups as I can to make sure I'm not on the fence about which category a new data point belongs to. At the heart of this process are what we call support vectors. These are special data points that sit right on the edge of each category. And they're the ones that actually define where that boundary or hyperplane should be drawn. In a way, support vectors are like the MVPs of the algorithm. They play the most crucial role in shaping how the model classifies data. Without them, SVM wouldn't be able to create that clear separation we're looking for. So, to sum it up, SVM works by drawing the most optimal boundary between categories of data, using those support vectors to help create the widest possible margin. This clear separation helps ensure that when you introduce new unseen data, the model can confidently and accurately classify it. Let's move on to some real-world application of support vector machines, or SVM. What's fascinating about SVM is its versatility. It's not just a one-trick pony. It can be used in a variety of fields, solving very different types of problems. Let's start with image recognition, One of the most common use cases for SVM is facial recognition. Think about the way your phone can unlock just by scanning your face. It's essentially using a classifier to recognize whether the image belongs to you or someone else. SVM plays a big role here by identifying the key features of your face and distinguishing them from someone else's. It's also used in handwriting recognition, like when your phone or tablet can figure out what you scribbled down. SVM works to classify different shapes and patterns to accurately distinguish between letters or numbers. Then we have text classification. This is a big one in the world of natural language processing, where SVM can be used to categorize all sorts of documents. Think of spam filters that separate junk emails from the important ones in your inbox. SVM analyzes the patterns in the text, looks for key indicators of spam, and makes its classification. It's also widely used for categorizing news articles, reviews, or even social media posts, helping to break down large sets of unstructured data into useful insights. Lastly, there's bioinformatics. This is where things get really exciting in terms of SVM's impact. In bioinformatics, researchers use SVM to identify patterns in genetic data. For instance, it can help classify whether someone is more likely to develop a certain disease based on their genetic markers. This application can be incredibly powerful in healthcare, enabling early detection of diseases and potentially informing more personalized treatments. So, as you can see, SVM is a pretty versatile tool. It's helping computers recognize faces, sort through documents, and even classify complex genetic data. It's amazing to see how this one algorithm can have such wide-reaching application across so many industries. Now that we've covered the application of support vector machines, let's take a step back and look at the key advantages and limitation of using SVM. Like any tool, SVM has its strengths and its weaknesses, and understanding both is critical for knowing when to apply it. So, let's start with the advantages. One major advantage of SVM is that it's highly effective in high-dimensional spaces. What does that mean? Well, in cases where your data has a lot of features, sometimes even hundreds or thousands, SVM is great at cutting through that complexity and finding those important boundaries. That's why it's often used for problems like image and text classification, where you're dealing with massive amounts of data with many different variables. Another big strength is that SVM can handle both classification and regression tasks. So, whether you're trying to sort data into categories like we've been discussing, or predict continuous values, SVM has you covered. It's a pretty flexible algorithm in that regard. And as we touched on earlier, SVM works really well when there's a clear boundary between the categories. If your data is nicely separable, SVM will do an excellent job of finding that optimal margin and making accurate predictions. Now, let's pause for a moment and shift gears to the limitation of SVM. While SVM is powerful, it does have a downside when it comes to large data sets. Processing time can become an issue. The algorithm requires a lot of computational power, especially when working with a lot of data points, which means it can become slow and resource intensive. This is something to consider if you're dealing with very large data sets where speed and efficiency are key. Another challenge is that SVM doesn't perform well when categories overlap significantly. If your data points from different categories are very mixed together, SVM can struggle to find a clear boundary. In these cases, other algorithms might outperform it. Finally, SVM requires careful tuning to perform at its best. This includes selecting the right kernel and adjusting hyperparameters like the regularization term. Without this fine-tuning, SVM can sometimes give suboptimal results. So, while SVM is a very effective tool in many situations, it's important to be aware of its limitations, especially in cases involving large data sets or overlapping categories.